Paper of the day is Consistency Analysis in Bloom, a calm and collected approach. Distributed programming is difficult for even experienced developers to get correct, understanding the trade-off between consistency, availability, and latency, while guaranteeing data correctness provides a wealth of problems for the application developer. This paper presents a language and method for programmatically verifying distributed consistency. Calm. There is a connection between distributed consistency algorithms and the logical monotonicity, that is, our programs must be correct even in the face of delay and reordering of messages and data across different nodes in a system. By designing programs with order independence, we can assure that logic of the system is maintained within a distributed environment. To understand this connection, consider two types of programs, monotonic and non-monotonic. Monotonic programs are those where the order of inputs to a system do not affect the output. In database terms, this includes selections, projections, and joins. Non-monotonic programs, on the other hand, are those where the order of inputs to a system does affect the output. Examples of this type of operations are groupings or aggregations. The authors make the observation that there is a tight relationship between consistency and monotonicity. Particularly, monotonic programs are guaranteed to be eventually consistent regardless of how computation or message deliveries are interleaved. In contrast, non-monotonic programs require coordination scheme that must wait until the inputs are complete before guaranteeing a correct output. This relationship is termed the calm principle, that is, consistency and logical monotonicity. Bloom. Traditional imperative programming assumes a logical order of statements that are executed in sequence. This model is a bad match to parallel and distributed systems, where ordering cannot be guaranteed except through expensive coordination algorithms. The authors present the Bloom language designed to model distributed algorithms that do not rely on order. The language uses unordered sets to represent state, and declarative rules model the computation to occur on these sets. Bloom is a purely declarative language that could be implemented using any other underlying evaluation engine to produce correct programs. Bloom programs are bundles of declarative statements about tuples. Each statement in Bloom is defined with respect to an atomic timestamp. Each timestamp, their facts are available as messages from outside system. Each statement uses available facts and tuples to derive new facts or tuples. Bloom also specifies how facts persist between timestamps. Each statement in Bloom defines the content of any derived collection of data. They can be viewed as inserting or accumulating results into collections. No mutable state is allowed, so no unknown side effects are allowed to exist outside of the statements and their facts. Bloom is similar in principle to Prolog, but geared towards distributed systems. Rather than rehash the syntax and semantics of Bloom, trusted readers are encouraged to consult the original research paper. The key takeaways are reasoning about logical time as part of the language and using declarative rather than imperative statements. A major contribution of the Bloom is the ability to perform analysis on a program to identify points of coordination. By viewing a Bloom program as a data flow graph, external inputs can be shown as sources, outputs as sinks, and collection of data as nodes within the graph. Computation rules are edges within the graph. By viewing the algorithm as a data flow graph, it is easy to visualize dependencies on data that require coordination between the multiple systems. Given the continued interest in distributed systems and the necessity to deploy distributed systems that meet the needs of growing datasets in the internet age, analysis and verification of distributed algorithms provide an enormous research potential. Bloom presents one such opportunity in this area. Personally, I get very excited about these tools and how they can be leveraged to design and develop correct distributed systems.